So on intergalactic problem number 18 for thermodynamics, it's a pretty straightforward question. You need to derive the amount of work done by an isotherm. And if you recall, an isotherm is something where the temperature is a constant. But that's the question. What is the work done by an isotherm? And this question's kind of annoying the first time you do it, simply because, well, an isotherm is a concave up curve like this. Which means that if I am trying to find the area from some initial point to some final point, I am trying to find the area of this curve, which there's only one way to do that. It's calc time. So what we can do here is we can do the following. I remember that this is a pressure volume graph, which means that work equals a pressure multiplied by a change of volume. Now this is true for an isobar, an isobaric function. That's our flat horizontal line. But what this also means to an extent is work equals the pressure multiplied by some small change in volume, some dV, like a thin little cube of volume in space. Now, this pressure here, while normally it was just a value for the isobar, this pressure can be a function. That pressure could change. So what can that pressure change with? Well, it could change with either temperatures or volumes. So if we can solve an equation for pressure as a function of volume, then I could put it on this graph. And we can actually do this. We know a pressure equation with a volume in it. We know PV equals nRT, which means that the pressure as a function of volume is just nRT over V. And technically, this would be like pressure as a function of volume if you wanted to write it all proper. But that nRT over V, that is the function that we can use there. So what we can say now is that, and I guess technically if we're writing this, there's an integral there because work is the integral of that. Anyways, we'll see that in a second. What we're going to have is nRT over V multiplied by dV. And if we integrate this, that will give us the amount of work done in this problem, or in an isotherm, along that curve. A fantastic thing about this is N, the number of moles, that's a constant. The ideal gas constant, R, 8.pi, or 8.314, that's a constant. On an isotherm, the temperature is a constant, which means that N, R, and T can all be pulled outside of this integral. So this integral just becomes nRT times the integral of dV over V. And this is going to go from some initial volume to some final volume. We don't know what those initials and finals are. It doesn't really matter. Who cares? They just exist. Now, if you've been in a calculus course, at this point in time, we're in, what month is it? End of February. Hopefully you would have seen at this point what a dx over x is as an integral. That's one of our special integrands that we should just kind of know off the top of our head, and we've even seen it a few times this year. So this integrand here will just become the natural log. And then when we do our top minus bottom, what we're going to have here is our constants nRT multiplied by the natural log of VF minus the natural log of VI. And then if we wanted to apply a fancy logarithm rule right here, we can say that this work equals nRT multiplied by the natural log of, well, when we subtract logs, that's really dividing by that quantity. So we can say this is VF over VI. And that is the work done by an isotherm. So this is finished. Ooh, that's not yellow. Finished! With this knowledge, you should be able to take care of problem 19 as well. Till next time, adios, and take it easy.